Today we're going to talk about valence electrons and ionic compounds. Valence electrons are the electrons in the highest occupied energy level of an element's atoms. We're talking about the outermost shell. Core electrons, by contrast, are the electrons in inner shells. The number of valence electrons that an element has determines the chemical properties of that element. To take a closer look at valence electrons, let's start by looking at this periodic table. Now, all elements in a particular group or family, that means column, have the same number of valence electrons. And this is what this particular version of the periodic table is trying to show. For main group elements, this number is equal to the group number of that element. In this table, the main group elements are labeled 1, 2, 3, 4, 5, 6, 7. The elements in the yellow block in the middle are transition metals. They aren't main group. The lanthanides and actinides, which are shown on most periodic tables, aren't shown in this table for the sake of space. Now, I want to clarify that even though it's in the column labeled 8, helium only has 2 valence electrons because it only has 2 electrons. Atoms like to have full outer shells. They tend to be the most stable when they have 8 electrons in their outermost shell and fill their p orbitals. This is one of the reasons that noble gases are so stable. They have full outer shells. Atoms want to have an s2p6 electron configuration. Atoms that have fewer than 8 electrons tend to give up or accept electrons so that the outer shell has the electron configuration of the nearest noble gas. One of the ways they do this is by forming ions and ionic bonds. This periodic table does a nice job naming some of the important parts of the periodic table, and this is why I included it. Let's look at some of these groups one by one. And to do this, we're going to use this lovely little animation here. We're going to start on the right side of the periodic table, and we'll look at the nonmetals, and nonmetals tend to gain electrons to form cations. We're going to look at the noble gases all the way over on the right. As you can see, they have full outer shells, a full octet. That means they have 8 valence electrons. This is a very stable arrangement for them. Noble gases are unreactive, which means they don't participate in chemical reactions. The halogens are to the left of them. These elements have 7 valence electrons, and this is a pretty unstable situation. They would be much happier if they had 8 electrons. So they're very reactive, and they tend to want to grab electrons from other atoms. To the left of that is the oxygen group. The oxygen group has 6 valence electrons. They are eager to gain 2 electrons so that they can have a full outer valence shell. And when they do this, they tend to form -2 charges. The nitrogen group is to the left of that. They have 5 valence electrons in that outer shell. They are very eager to gain 3 electrons so that they can have a full outer valence shell. When they do this, they form ions with a 3- charge. The carbon group is to the left of this. As you can see, carbons are in the middle of the row. They don't typically form ions, but when they do, they tend to form ones with a 4+ or a 4-. Now, let's go to the left side of the periodic table. This is where the metals are. Metals tend to lose electrons to form cations. All the way to the left is the alkali metals group. These elements have 1 valence electron, and it's very easy for them to lose an electron because if they do, they will have a full outer valence shell. They will have a complete octet, and this makes them very stable. Hydrogen, also in this column, is an exception. Hydrogen only has 1 electron. It's very easy for it to lose an electron to become a proton, or to gain one so that it has a 1s2 electron configuration like helium. The hydrogen anion and the helium atom only have 2 electrons in their outer valence shell. The alkaline earth metals are just to the right of the alkali metals. These have 2 valence electrons. Now, if they lose 2 electrons, they'll have a full outer valence shell, and so they typically form cations that have a 2+ charge. To the right of that, just on the other side of the transition metals, is the boron group. The atoms in this group have 3 valence electrons, and if they lose these electrons, they will form a 3+ charge. Now let's look at those transition metals in the middle. Transition metals have variable charges. Let's look at iron, for example. Sometimes iron will lose 2 electrons to become iron 2+, and sometimes it loses 3 electrons to become iron 3+. This is why we need to use Roman numerals when we name compounds that have transition metals in them. We need to specify the charge. Remember that transition metals are d block elements. This means they have d orbitals. Since d orbital electrons are in an inner shell, many people don't consider them to be true valence electrons. Remember that when these transition metals form ions, they tend to lose their s electrons first because those are in an outer shell. However, after they have lost their s electrons, some transition metals will go on to lose a couple of d orbital electrons, and this can create ions with different charges. This is what happens with iron. There are a couple of special transition metals that deserve mentioning. Silver always forms an ion with a 1+ charge. Zinc always forms an ion with a 2+ charge. And aluminum always forms an ion with a 3+ charge. So when we're naming compounds involving those 3 cations, we usually don't have to put a Roman numeral after the cation. Now let's talk about ionic bonding. Many elements tend to lose or gain enough electrons to have full outer shells, and one way they can do this is to take electrons from or give electrons to other atoms. When they gain electrons, they become anions, and if they lose electrons, they become cations. Anions and cations attract each other through electrostatic forces. The negatively charged electrons on one ion tend to be attracted to the positively charged nucleus of the other to form an ionic bond. Ionic bonds happen between metals and nonmetals. Ions can have one atom, or they can be polyatomic with several atoms. Most polyatomic ions are anions. Hydronium and ammonium are the exceptions. They are common cations. Elements in the same family have similar properties. This is because they have the same number of valence electrons, and the valence electrons determine how an atom is going to react with other atoms. For example, all of the ions in the alkali metals have a 1+ charge, and they're all very reactive with water. Potassium chloride and sodium chloride, each of which has an alkali metal cation, these both play important roles in the chemistry of the body. In fact, potassium chloride is sometimes used as a salt substitute. Elements in the same family tend to form compounds that have similar formulas. For example, if we look at the alkali metals with the 1+ charge, we might see things with an XY configuration, such as sodium fluoride, potassium chloride, lithium chloride, or with an X2Z configuration like sodium oxide, potassium oxide, etc. If you look at the alkaline earth metals with a 2+ charge, they also tend to form compounds that have similar formulas. So you will see these sorts of patterns. So let's summarize. The outer electrons are called valence electrons. All the elements in a particular group or family have the same number of valence electrons, especially when we are talking about main group elements. Atoms tend to be the most stable when they have full outer shells. We call that a full octet. One way they can get full outer shells is by forming ions and forming ionic compounds. Sometimes atoms do this by giving away electrons or taking them from other atoms. The number of electrons an atom will gain or lose depends on how many valence electrons it has. The likelihood that two elements will form a chemical bond is determined by the interactions between the valence electrons and the nuclei of the elements they're bonding with. Elements in the same column of the periodic table tend to form analogous compounds.